My name is Nihar Perry, and I'm excited to share our work, an empirical analysis of range for 3D object detection. Despite the maturity of 3D object detectors in existing literature, most treat detection range as a constant instead of an adjustable hyperparameter, likely because existing benchmarks primarily evaluate near-field detections. Kitty only evaluates annotations up to 70 meters using a front-facing LiDAR, NewScenes annotates up to 50 meters, and Waymo annotates up to 75 meters. In this work, we focus on Argoverse 2, which annotates objects up to 200 meters, but only evaluates detections up to 150 meters. Motivated by highway driving and long horizon planning, we present an empirical analysis of far-range perception and share insights that are widely applicable across model architectures. Contemporary solutions for near-field 3D detection make use of 3D voxel representations, often encoded with a bird's-eye view feature map. While quite intuitive, such representations scale quadratically with the spatial range of the map. We find that a primary challenge for effectively addressing long-range 3D detection is managing compute and latency demands, and study different factors for trading off compute versus latency, like voxel resolution and detection range. Bird's-eye view-based detectors operate on a dense 2D feature map, whose spatial dimensions are directly determined by the processing range and the voxel size. Interestingly, the existing literature on 2D detection has converged on image resolution and backbone depth as the handy knobs for trading off accuracy versus latency. We revisit these questions in the context of 3D detection. Properly tuning the detection range together with voxel size can yield a better performance latency trade-off. We train range experts by tuning the range parameter and evaluating the accuracy and latency across different range intervals. In this example, we've trained a 100-meter point pillars range expert represented by the orange dot. Although models may not report detections for the full range, we evaluate all models at the full range. Since the baseline detector is fully convolutional, we can run inference at a different range from training. Taking this into consideration, we introduce a new notation shown below. For example, 100 represents the range the model is trained at, 4 represents the reciprocal of the voxel size, and 50 represents the inference range. Note that the voxel size must remain the same during training and testing. We plot the performance of our model evaluated at different ranges using a blue curve. Training a 100-meter range expert with twice the voxel size, shown as a yellow triangle, provides a modest improvement in latency, but dramatically reduces performance. Running our 100-meter range expert at 200 meters results in almost no performance increase, but dramatically increases latency by a factor of 4. Even if the dataset includes object annotations up to 200 meters, Pareto optimal accuracy versus latency trade-offs may be achieved by artificially limiting the range of the model to 100 meters, essentially giving up on far-field detections during training. We posit that this is due to the distribution of annotations, with fewer objects being labeled in the far field. In summary, we find that range is the single most effective parameter for trading off latency and accuracy. Ultimately, we'd like to avoid giving up on far-field detections, as it's important for highway driving and long horizon planning. To avoid doing so, we simply combine range experts by ensembling. Specifically, we combine the 0 to 50 meter detections from the 50-meter range expert with 50 to 100 meter detections from the 100-meter expert and 100 to 150-meter detections from the 150-meter expert. We find that such an ensemble greatly boosts detection accuracy. Perhaps unsurprisingly, this works well because it exploits a well-known but underemphasized property of LiDAR. Farther range implies greater sparsity. However, it requires that we run 3 models, and this is incredibly slow. We can trivially speed up a multi-range ensemble with range-specific asynchronous processing. We take inspiration from hierarchical slow-fast planners that run a low-frequency planner together with a high-frequency reactive controller. From a perception perspective, autonomous agents need to quickly react to near-field objects to avoid potential collisions, while far-field objects may be used for more strategic long-term planning. Concretely, we run near-range experts at high frequency and run far-range experts at a lower frequency. Our results highlight an interesting observation. Sometimes it's more effective to forecast the location of a far-field object from a previous frame's detection than to directly process the far field of the current frame. One reason is that the object may have appeared in the near field of the previous frame, making it easier to detect. We find that near-far ensembles reduce runtime by 33% with little performance decrease. In order to maximize the performance of far-field range experts, one may naturally assume that allocating model capacity to near-field regions of the LiDAR sweep may negatively impact model performance. Concretely, when running inference with a 100-meter range expert to detect objects between 50 and 100 meters, it seems wasteful to spend processing time on the 0 to 50-meter region of the point cloud. To address this concern, we run range experts with a masked-out donut hole. This donut hole mask does not negatively affect detection accuracy, but also provides a modest speedup because it makes better use of sparse computation. However, it's important to note that the speedup is largely dependent on the sparse voxelization encoder. We find that this provides considerable improvements for models using SPConv 1.0, but limited improvements for models using SPConv 2.0. Putting everything together, we find that simply running near-far ensembles with donut hole cropping preserves much of the performance of our naive range ensemble at a fraction of the runtime. Lastly, we evaluate the far-field generalization across 4 popular detectors and find that some models generalize well across ranges, some generalize poorly, and some don't generalize at all. We examine these trends through the lens of model architecture and training losses. First, we note that point pillars has some generalization capability across ranges. Notably, when we evaluate a 100-meter range expert at 150 meters, the performance does not change, indicating that the model likely predicts all far-field detections with a lower confidence than near-field detections. We argue that knowing what you don't know is a form of generalization. Second, CBGS is architecturally identical to Centerpoint, but uses a voxel net encoder instead of a point net encoder. Unlike point pillars, CBGS predicts far-field detections with higher confidence than some near-field detections, resulting in lower performance when evaluating long-range detections. We hypothesize that point pillar's point net encoder captures local features that generalize better than the global features encoded by voxelnet. Next, we consider the surprising across-range generalization capabilities of Centerpoint. Centerpoint is architecturally identical to CBGS, but uses a center regression head instead of an anchor-based detection head. Although these are architecturally similar, we posit that the difference in training loss significantly impacts generalization. CBGS attempts to maximize the IOU of its predictions with the ground truth. In contrast, Centerpoint learns to regress a heat map of Gaussian targets. We hypothesize that these soft targets act as a form of data augmentation, which makes it easier to train the model. Lastly, we consider transfusion, which does not generalize across range at all. Specifically, although we observe strong performance for the 100-meter range expert when evaluating at 100 meters, we notice that performance drops to nearly 0 CDS when run on either 50 or 150-meter ranges. Transfusion is architecturally identical to Centerpoint, but uses a Detter-like transformer decoder as a detector head. We posit that using metric positions for positional encoding rather than relative positions may yield better across-range generalization. Long-range 3D detection remains a challenging problem that requires further exploration. Our best range expert only achieves 6.5 CDS between 100 and 150 meters. Therefore, we urge the community to continue to explore far-field detection, as it has important safety implications for highway driving and long-horizon planning. For more information about our work, please check out our full paper.